So, hello to everyone. We can continue our conference of smart innovation in energy and mechanical systems. So today it's the second day of the conference, and we continue to work in framework of the session 2, which is devoted to the topic of artificial intelligence and digital technologies in engineering. So, and I would like to introduce to your attention the first scientific report on the topic synergy of blockchain and artificial intelligence for the decentralized smart energy management of the authors Volodymyr Pavlenko, Igor Ponomarenko, Oksana Margulets, Dmitro Ponomarenko, and Dmitro Danilchenko. So let's start the first presentation.
Hello, dear colleagues. Can I share my presentation?
No,
We have the video record of your presentation, so I think that we will start the video records, and after that we will set you. There will be some questions.
Thank you.
Thank you too.
Topic of this research is the synergy of blockchain and artificial intelligence for decentralized smart energy management by Igor Ponomarenko, Volodymyr Pavlenko, Oksana Margulets, Dmitro Ponomarenko, and Dmitro Danilchenko. The integration of blockchain and artificial intelligence into smart grid technologies make it possible to create effective information systems that, based on high quality and protected information, contribute to the identification of optimal solutions for supporting the generation and distribution of electricity, the possibility of constant learning and determination of the best options for the functioning of energy systems in populated areas characterized machine learning algorithms. This study aims to explore the integration of blockchain and artificial intelligence in decentralized smart energy management, focusing on optimizing energy distribution, enhancing system security, and improving efficiency in smart grid technologies. The research examines a smart grid architecture model, emphasizes the role of AI-driven adaptive algorithms and blockchain-based transparent transactions in urban energy systems. From the management's point of view, it's advisable to monitor modern energy systems based on the technical characteristics of the networks, and special attention should be paid to the information system used. The physical characteristics of the power network require specific management methods by established standards, and hierarchical zones are characterized by specialized management. Smart grid consists of 5 main elements: generation, transmission, distribution, distributed energy resources, and customer premises. On the other hand, power system management consists of 6 elements. The environment of the energy system makes it possible to monitor the interaction between the existing elements. Smart grid plane domains and zones of smart grid architecture models. Smart grid architecture model, or SGAM domains. First, generation. Production thanks to traditional producers of significant volumes of electricity by the needs of consumers at the national and international levels. Second, transmission infrastructure, highways for moving electricity in a certain area. Next, distribution infrastructure, highways for moving electricity to consumers. Fourth, distributed energy resources, or DER, distributed electricity at the level of local energy systems, which unit producers and consumers of electricity at the local level, domestic, commercial, and industrial use. Transmission system operator, or TSO, distribution system operator, or DSO, balance responsibility party, or BRP, are used to control the distribution of generated electricity. Next, customer premises includes local electricity producers and consumers at the level of individual households. In the business sector, there are a large number of companies producing goods and providing services, as well as local governments and utilities, which generate significant electricity demand. The smart grid architecture model structure arose due to the compilation of compatibility levels with the presented intelligent network system, the location of which of the layers is regulated, which allows the smart grid to function effectively. The given architecture responds to the specific of the sector and is built by the scientific principles of expediency. The existing model consists of the three levels: smart grid architecture model domains, zones, and last, interoperability layers. Modern cities are constantly developing their energy systems, both quantitatively and qualitatively. The expansion of agglomeration in the context of urbanization leads to the need to create the power of energy system with high increase and the corresponding increase in communications. Along with this, innovative technologies are gradually being introduced to optimize key processes and achieve the necessary level of energy efficiency. Energy management makes it possible to effectively manage smart grids in smart cities and respond quickly to change in electricity consumption. Considering the complexity of the structure of smart grids in large cities, the management system must be implemented in accordance with modern scientific approaches and be based on the use of advanced information technologies that automatically adjust set parameters. The use of blockchain technology is gaining popularity in many types of economic activity, which is due to the high level of reliability of transactions using the presented technology. For smart cities, as center of innovative technologies, concentration blockchain allows for a large number of benefits, including optimizing of the city's energy system functioning. Smart cities are actively implementing the use of artificial intelligence to optimize information technology within relevant systems, including the energy sector. The presence of a significant number of specialized machine learning algorithms allow for solving various optimization tasks for smart grid technologies. Among the important tasks of complex energy systems in smart cities, it's necessary to pay attention to ensuring the economic efficiency and meeting the needs of a large number of various consumers. Conclusions. Smart grid technologies are developing in an inextricable connection with the field of information technology, including servers for storing and processing big data, the availability of high-performance mathematical algorithms, primarily artificial intelligence, allows for a comprehensive assessment of complex energy systems in smart cities. The creation of modern energy management involves the information of an effective information system, which, based on a set of data sources, allows for an objective assessment of key processes. Smart cities are characterized by a modern digital environment, which includes cameras and sensors that allow energy systems to be monitored based on a selected indicator system. The active development of blockchain and artificial intelligence algorithms lead to the formation of qualitatively new approaches to monitoring and managing the digital environment of energy systems in smart cities. Tracking advanced technologies and accessing the expediency of their use in smart grids is an important area of activity for specialized institutions in smart cities. Qualitative transformation of energy systems in agglomerations make it possible to significantly increase the efficiency of their functioning and ensure the achievement of the declared goals of sustainable development. Thank you for watching us. Stay safe and have a good day.
So thank you. Thank you very much for your report. And are there any questions from the auditory to the authors of the paper? If no, we have a few questions to you. So the first one is, how realistic is the implementation of your model in terms of the existing urban infrastructure?
Can you hear me?
Yes, we can hear you.
Just a minute. Based on your question, I think we can use different smart grid technologies, which in the modern world are popular. First of all, IoT devices and sensors. So these gadgets are very popular, and we can use these gadgets to implement in different areas. For example, I am associated professor of marketing, and we can use IoT smart meters, phasers measurements, wireless sensors. Also, another group, communication protocols and networks also are very popular in the modern technologies. First of all, 5G connectivity, AI and data analytics also are very popular. In briefly, if talk about your question.
Yes, thank you very much.
Thank you.
Hello.
Next question. Have you studied the potential security or data privacy risks of such an energy system?
Okay, thank you for your question. We don't study this question. We talk about the problem of privacy because it's very important in the modern digital environment, but we have no practical experiments about this problem.
Thank you.
Okay, thank you. Maybe it can be like the topic for your future research, so you can continue your research and maybe speak about this topic too in future. So thank you very much.
Thank you.
We can continue our conference. So the next scientific report will be on the topic web-based control system for laboratory electromechanical elevator installation from the authors Grigory Дяченко, Ivan Laktionov, Dmitro Yakupov, Roman Borovik, I'm sorry, and Alexei Yalansky. So we will start your record, and then we'll have some questions. So.
Welcome everyone. I am honored to present our research on the development of a web-based control system for a laboratory electromechanical elevator installation. This system was designed to enhance practical training in engineering education and bring real-world automation closer to students. Here is a brief roadmap of today's talk. We will begin with the motivation behind our work, followed by the aim and scope of our research. Then I walk you through the system architecture and algorithmic design, present the results, and wrap up with conclusions and future directions. Laboratory training is an integral part of applied engineering research and training in technical specialties, and the availability of modern equipment is a prerequisite for sound and up-to-date practical training, which allows for the experimental reproduction of theoretical relationships. The international cooperation within the framework of Laboratories Across Borders project between the Dnipro University of Technology and the German partner Rotterdam University is aimed at solving the problem faced by many Ukrainian universities, in particular due to budgetary constraints as well as military operations, which is why training takes place in a remote format and the laboratory base is either absent or has been destroyed. A resource-saving and innovative approach to cooperation is to order, monitor, and support various practical laboratory experiments in both locations via remote access, thus avoiding investment in duplicate laboratory equipment. Our aim was to develop and test a web-enabled control platform for an elevator installation used in lab settings. The object of research was the information processes flow in such systems, and the subject focused on the software and hardware enabling this remote control environment. This is a very simplified use case diagram to illustrate the interaction between the student user and our web-based control system for laboratory experiments. The process begins with authorization on our platform, followed by assessing the experiment guidelines. From there, student can read the experiment description, edit parameters, and start the experiment. So the system includes built-in check-ins for parameter validation and allows the experiment to be stopped either manually or automatically. After completing the task, students can generate a PDF of their results, and this structure ensures a smooth, secure, and educational remote experiment experience while maintaining close alignment with real-world lab procedure. On this diagram, it is shown the architecture of our setup. We built a lab-scale elevator system using real industrial components like programmable logical controller, variable frequency drive, IP camera, and Raspberry Pi, as well as remote input-outputs. So all these are integrated via protocols like Modbus, CAN-Open, and TCP/IP. This provides an authentic industrial experience. Now, this diagram presents the full communication map of the remote laboratory system. So starting from the right, the student's computer runs a web application where they assess the experiment interface and send commands and visualize the results. So all data transfers between components securely across the layers from hardware to the cloud using standard protocols like HTTP, WebSockets, and HTTPS, ensuring reliable and safe communication. So on the left, we have the core industrial hardware like the PLC, VTF, I/O modules. So these components interact via Modbus and CAN-Open protocols. And all this field equipment connects to WebHMI, which acts as a main controller. And on Raspberry Pi, we have server running on Node.js and WebSockets to ensure queued and time-limited access. So it interfaces with both the experiment hardware and the WebHMI server, which executes service and scripts to provide real-time data. And the final part is the proxy server hosted on NMU ORQA, which handles secure port forwarding and acts as a gateway between internal systems and the student's browser. Users can access the system through a browser, so after authentication via Moodle, they are redirected to this landing page where they can gain control over the system, obtaining the master role if the system is not occupied by someone else, or entering a waitlist or the queue. So the results of the experiments then can be saved as the PDF report, as mentioned earlier. And this is the user interface of the experiment control system itself. So it includes the modules for controlling the elevator, tuning motor parameters, monitoring real-time system status, and viewing live video stream from the IP camera. It was designed to be intuitive, functional, and educational rich for a fully immersive experience. So as a result of the research conducted in this paper, an urgent scientific and applied problem has been solved in the creation, debugging, and validation of the operational modes of a web-based control system for a laboratory electromechanical elevator installation. So the key technical aspects of web-based control of electromechanical objects, particularly the interaction of software with the hardware of the elevator installation, have been identified, which made it possible to solve problems related to network communication, optimization of information and communication processes, and ensuring reliability of operation. So software for remote control of the laboratory test bench has been developed and implemented, and software that provides an ergonomic interface for remote access and control of all the aspects of the installation has been created and tested. So an extended range of functionalities has been developed and implemented, such as remote start-stop of the plant, system status monitoring, collection and analysis of plant operation data, and development of the down collective operation algorithm, which made it possible to implement effective remote control and rapid response to the events. Thank you for your attention. If you like to try out the system or collaborate, feel free to contact me or visit the project page via the QR code online. I'm happy to take any questions now. Thank you.
So
Thank you.
Yeah, thank you very much for your interesting scientific report, for your paper. So is there any question from the auditory? So if no, then we would like to ask you, so the question is, so it's today it's absolutely clear that in wartime it's very important for students to have this possibility to conduct some laboratory work in distant way. So the question is it possible to provide such distant connection in this laboratory stand? And if so, what are the necessary conditions for this?
Good day to you. Again, thank you for the question. So as for the question itself, so it was the aim, like the absolute aim of this research to give a remote access. So it's not like we can connect to it only from the lab which is in the university, but you can connect it to like from any point in the world where you have internet access. And it's available almost 24/7, or at least in the working hours of the university. So any student from any university can access it. So yeah, thank you.
Yeah, thank you.
And my question, is there a possibility for students to change the regulator coefficient or the type of regulator during research? How can this be implemented?
Okay, thank you very much. So this possibility is given. So in the web interface, so the control system of the elevator, where a student can control and monitor the status, it is implemented in WebHMI that has internal web server. And in this GUI that was shown on one of the slides, we give the possibility to change the parameters. So, but this change, like what you can change is limited by us in to get along with safety requirements. But what students can do, they can play with the internal speed control loop of the given variable frequency drive. So there is a PI controller, and also the block where you can change the ramp parameters, like how fast you should accelerate, decelerate, what speed you want to reach, and also you can change the parameters from proportional and integral parts. And then the parameters entered are checked by the scripts to like adjust them within the allowed ranges, and then these control signals are forwarded to the system, and we give the expected results.
Thank you.
Okay, yeah, thank you very much. Thank you for your answers and for your report. So
Thank
let's
you.
continue. And the next presentation on the topic, consideration of the CVSS-based metrics in building a mathematical routing model concerning road vulnerabilities for engineering systems. Of the authors, Ганна Плехова, Сергей Неронов, Тетяна Волкова, Наталья Птица, and Volodymyr Kuzhelь. So again, we have the video records of your presentation. We will start it, and then we will. There will be some questions.
I'd like to present you a report, consideration of the CVSS-based metrics in building a mathematical routing model concerning road vulnerabilities for engineering systems. Authors Ганна Плехова, Sergei Neronov, Tetiana Volkova, Natalia Ptitsa, and today's speaker Volodymyr Kuzhelь. Introduction and the major challenges. I should say that using common vulnerability scoring system to access cybersecurity is very important in engineering systems. This CVSS model is used, which allows for regular analysis and assessment of potential vulnerabilities in software and network equipment. During a regular audit, a critical vulnerability of the SDN controller was discovered. Using SVSS, specialists determine the level of criticality which requires immediate response. SDN allows you to quickly reprogram flows in real time, isolate the affected network segment, minimizing the impact of the vulnerability on the overall infrastructure until the problem is completely fixed. Thus, such an integrated approach to the application of smart manufacturing SDN and security assessment using CVSS allows enterprises to effectively manage risks, optimize production processes, and ensure a high level of security of the Industry 4.0 infrastructure. Aim and the research tasks. We want to propose an enhanced solution for calculating the weighting factors used in the routing decision process. Unlike the time and environment metrics, we choose basic metrics to characterize the existing vulnerabilities of network elements. The objective of this study is to enhance the secure routing model by integrating the basic CVSS indicators and addressing the technical challenges of selecting the optimal route, which is based on the composite indicator that includes both the basic CVSS metric and the bandwidth of the communication channels involved. The research methodology involves analytical modeling, formalization, and comparison. Understanding the common vulnerability scoring system enables the assessment of a wide range of vulnerability affecting systems. The systematic framework for vulnerability assessment provided by CVSS is beneficial for developing similar systematic approaches not only for physical infrastructure, but also for other types of vulnerabilities, such as those related to organizational issues, policies, and procedures. CVSS is a widely accepted method. For instance, it's recommended for quantifying the vulnerability level of network equipment. I should say that each national vulnerability database records contains the following information: the unique dictionary of common names for security vulnerabilities or exposures, known as common vulnerabilities and exposures, a vulnerability description, website links related to the vulnerabilities, and CVSS metrics. The goal was to enhance the mathematical model of secure routing in relation of CVSS-based metrics. The issue of secure routing with load balancing was framed as an optimization problem with an optimization criterion. When applying the security protocol for reliable data delivery scheme, the following issues need to be addressed to ensure secure routing of messages in the network. 1. Compute a set of non-crossing rows between given nodes, senders, and receivers. 2. Split the sent secret message into many parts. And 3. Assign a set of message fragments to set of routes defined in step 1. 4. Methods and models for protecting engineering systems networks by routing confidential. I'd like to propose two methods. First method is based on an optimization process that selected a set of composite paths and uses them to balance the portions of the message to be transmitted, providing an acceptable value for the probability of that compromise. Considering the possibility of using composite path, the use of this method within the given calculation example reduced the leakage probability of the transmitted messages from 5–10% to 25–50% on average. The second method is related to the need to quickly calculate and change the set of paths used to transmit some of the sensitive messages when the network conditions change due to a security breach. Thus, approaches and mechanisms for fast rerouting with local or global protection of network elements can be considered as an implementation of reactive approach to secure routing technologies. Experiments. In accordance with the recommendation above, for each of these metrics, the impact of vulnerability exploitation can be characterized as follows: none, partial, complete. You can see table 1 metric values to calculate the base score for network node vulnerabilities, and we can find these three characteristics in this table: none, partial, and complete. In table 2, describe the base matrix characters the overall exploitability of particular vulnerability. We can find different type of authentication such as multiple single none and different type of access complexity, higher, medium and low. Results. We propose to improve the existing secure routing model by considering the basic matrix of vulnerability criteria. We will conduct a study of comparative analysis and the considered models, and for the modified flow model of secure QoS routing, we will prove its operability, quantity and effectiveness of application within the framework of computational examples. For this example, the structure of the communication network was chosen, representing the data plane of the SDN network shown in Figure 1. The network consists of 5 routers and 7 communicational channels. And also in Table 3, each router of the network corresponded to the special description of the existing vulnerability according to the database of well-known information security vulnerabilities, common vulnerabilities and exposures. And now we can see Table 3, characteristics of network equipment vulnerabilities for research, and Figure 1, the studied fragment of the network structure. Conclusions. The mathematical model of secure routing has been updated, integrating the basic assessment of the vulnerability critically. The technological task is formulated as an optimization problem with a quadratic objective function, where the optimal route is selected according to the combined metric that takes into account both the basic assessment of vulnerability critically and the throughput of the network links that form it. A comparative analysis was conducted. The existing secure routing model was compared with quality of service routing model that use metric similar of the OSPF protocol, as well as with a new secure quality of service routing model that takes into account the main indicators of vulnerability critically. The results confirm the effectiveness of adequacy and the proposal model. Thank you. You can find my contacts on this slide. Bye-bye.
Vladimir, I have a question.
Just a second. I will ask the auditory. That's okay. So let's continue. We don't say you bye-bye, so we continue our conference and we have some questions. But before our questions, I would like to ask if are there any questions from the auditory? If no, then we can ask.
Hello to everyone. Bye-bye was too early. I agree with you.
So yeah, then we have some questions from organized committee.
Vladimir, how does your proposed model improve network security compared to traditional routing methods?
Thank you for your question. I should say that proposed model combines elements of QoS assessment using CVSS, as you know, and unlike traditional models, this model can integrate security indicators into the routing process and uses a combination of throughput and security metrics, supports multipath routing with dynamic load balancing, and this model uses both preventive and reactive protection methods. Thank you.
Thank you for your answer. And another one question is, are there any limitations or constraints in using your model with the existing SDN infrastructure?
Thank you for your question. Yes, sure. This model is compatible with the general principles of the SDN architecture, but it has several technical and practical limitations, such as the limitation on the computing resources of the SDN controller, the need for constant updating for the CVE, CVSS database, the need for accurate profiling of network nodes, and delays due to the complexity of the optimization problem. And the last one, compatibility limitation with some existing SDN protocols. I'm sorry. Thank you.
Thank you.
Okay, thank you very much. Thank you for your answers. And the one of the last presentations for this section today is the prediction of anti-friction characteristics of epoxy furan coatings using an artificial neural network from authors Petro Stupляк, Oleg Yasny, Oleg Totosko, and Danilo Stupляк.
Dear listeners, my name is Danilo Stupляк. For your attention is presented presentation for article Prediction of Artificial Characteristics of Epoxy furan coating using an Artificial Neural Network by authors Petro Stupляк, Oleg Yasny, Oleg Totosko, and Danilo Stupляk. Industries such as transporting, energy, instrument, and manufacturing are important to developed societies. The surfaces of many moving machines, parts in their industries interact with each other, so wear and friction are necessary. So it is very important to make them resistant to wear. For many years, steel has been one of the most common materials for manufacturing machines, parts, and machinery due to its low cost, ease of manufacturing, and design flexibility. However, the wear resistance of surface properties of steel are not very good. Therefore, it is necessary to improve the surface properties of steel parts designed to operate the harsh environment associated with high level of wear. The application of surface coating is one of the most useful methods available to improve the surface properties of steel. Surface coating are used in many areas where metal surface and subjected to several wear and tear. Neural networks play a key role in the study of polymer composites with various additives helping to predict their properties and process experimental data. It is known that the machine learning uses data mining to build mean relationships between material composition and its properties. The approach is particularly effective in the study of polymeric composite materials based on rhodoplastics, in particular with epoxy furan coating. It is important to note that the accuracy of the system depends on the parameters chosen for neural networks. In general, using machine learning algorithms, in particular neural networks, it is possible to model the properties of polymer composites with great accuracy. One of the main advantages of this approach is the possibility of non-destructive testing, which allows obtain results without affecting the structure of the epoxy composite. It can also be noted that the neural networks are one of the most widespread machine learning methods. In particular, the prerequisite for their emergence was the study of the function of the human nervous system. In general, a neural network is a system with a large number of neurons that can approximate rather complex dependence of find patterns between input and output data. In this slide, at first figure, you can see the dependence of the predicted friction coefficient on the filler concentration in the composite and temperature. The second figure, you can see the dependence of linear wear rate of the epoxy furan coating on the filler concentration in the composite and temperature. So in the third is dependence of temperature in the friction zone of the epoxy furan coating on the filler concentration in the composite and temperature. Modification of epoxy materials with disperse polyethylene mixed with mineral oil leads to a shift of the minimum on the curve of dependence of wear intensity of epoxy content of region of their content of 20 per 35 mass fraction of dispersed polyethylene per 100 mass fraction of binder. The temperature of the friction surface of the modified epoxy composite materials in the entire studies range of filler concentration changed slightly and lies below the glass transition temperature of the polymer matrix, which is the range of 383 413 kelvins, depending on the heat temperature technologies. In this slide, you can see the value of technical characteristics of parameters of neural network used for modeling. You can see that for friction coefficient and temperature in the friction zone, we used the neural network MLP 291, and for intensivity of linear wear MLP 281. Also, the learning algorithm is BFGS for all of values, and the error evaluation metric was SOS. So the hidden activation function was logistic for friction coefficient and intensivity on linear wear, and tangential with the temperature in the friction zone. And its outgoing activation function was exponential for intensity of linear wear and logistic for temperature in the friction zone. For more meaning definition and analysis when observing the residual values error, histograms are shown for the predicted values for each characteristics. For friction coefficient, for the wear level, and the temperature in the friction zone. The error values were calculated separately for each characteristic to assess the effectiveness of using the artificial neural network method. So the conclusion is that in this work, neural networks were used to create models to evaluate their use in analyzing the tribotechnical characteristics of epoxy furan composite, which are often used in industry to produce wear-resistant protective coating. This research helped to reduce the time and cost with expensive tribotechnical testing of materials. Prediction of characteristics from experimental data was achieved by using a model created with the help of neural network. The dataset used in this study was obtained by approximating the result of tribotechnical characteristic studies. The results obtained are in good agreement with experimental data. The prediction error of neural network is 0.2, 0.63, and 0.78% in the test samples. The obtained result will allow creating conditions for targeted regulation of tribotechnical characteristics due to the scientific and structural organization in the formatting of materials. The results of research using neural network have proved the effectiveness of machine learning algorithm for predicting the tribotechnical characteristics of composite based on epoxy furan material under specific test condition. Thank you for your attention.
Yes, thank you very much. And let's move on to the questions. So are there any questions from the auditory? So we have, as usual, questions.
My question, how versatile is the build model? Can it be used for other type of coating?
This, thank you for question. Well, this model was developed for this particular coating and this particular filler. But however, with input data, we can train the neural network for any other coating with other fillers. Neural network analysis allows us to find a pattern in data of various characteristics with different physical structures.
Thank you. And one more question. Which input parameters were most influential in predicting wear?
Well, thank you for question. The parameter that influenced the change in the coefficient of linear wear, the temperature in the friction zone, and coefficient of friction were the amount of filler and pressure during the experiment. There were the input parameters that we analyzed with neural networks.
Thank you.
Yes, thank you very much for your answers. So let's continue. And we almost reached to the end of the session 2. We have only one presentation that we that we have to listen. So the topic of the last presentation for the session 2 is smart technologies for greenhouse climate control. Of the authors Mikhail Zaluzhny, Olena Nazarova, Alexander Maley, and Natalia Furmanova.
Good afternoon, dear colleagues. My name is Olena Nazarova, and I'm presenting a research on the topic Smart Technologies for Greenhouse Climate Control. The impact of global warming is uneven across the globe. Ukraine is already feeling the effects of climate change. 2020 was the hottest year on record in Europe and Ukraine, exceeding the 1961 to 1990 average by 2.8 degrees. The slide shows the changes in abnormal temperatures over the year. Ukrainians' main export is agricultural products. The development of agriculture in the form of smart greenhouses is considered as an alternative way to overcome the food crisis due to population growth, climate change, and environmental pollutions. For Ukraine, this scientific direction is relevant due to the loss of the ability to use a significant number of land plots as a result of military operations in the southeastern region of the country. Smart technologies for greenhouse climate control contribute to a green economy by optimizing resource use through automated humidity, temperature, and carbon dioxide monitoring systems, reducing energy consumption and water loss. The integration of IoT, artificial intelligence, and renewable energy sources allows for increased yield with minimal environmental impact, contributing to sustainable agriculture, which confirms the relevance of the research topic. The aim of the work is to develop a prototype of a microclimate monitoring system for smart greenhouses based on Internet of Things technology, which provides the necessary conditions for growing plants while simultaneously reducing energy consumption and minimizing environmental impact. The acquired skills in developing devices using wireless networks and creating dashboards for visualization of the monitoring system should be introduced into teaching in relevant courses and diplomas. Greenhouse farms occupy vast areas may have several areas and may greenhouses. For example, in Ukraine during 2023, grants for the development of greenhouse farming is the amount of 159.4 Ukrainian hryvnias million were issued. Therefore, automation using modern monitoring system using IoT technologies based on smart electronics is more relevant. IoT opens up new opportunities for automation, optimization, and monitoring of various processes. Thanks to sensors, you can presently adjust environmental parameters, temperature, humidity, light level. This allows you to create ideal conditions for plant growth, which in turn helps to increase yield. Automatic irrigation, lighting, ventilation, and heating systems can operate without human intervention, which reduces the risk of errors and increases work efficiency. The temperature in the greenhouse is distributed non-linearly and unevenly both in a plane and in height. The temperature should be measured at least at 2 points in the soil at a depth of 10 to 15 centimeters and at the height of the plant and at 2 intersections 6 to 8 meters from the site. From the point of view of location and use, it is convenient when the sensors have an independent power source and wireless communication. Tunnel greenhouses are the most common in Ukraine. The size of industrial greenhouses starts from 10 weight, 15 length, and 6 meters height. And greenhouses enterprises uses dozens or hundreds of greenhouses. Greenhouses can be interconnected too. IoT sensors are a key component of Internet of Things systems that collect data from the environment and can measure various parameters such as temperature or geolocation. IoT networks are various communication technologies to transmit data, among which LTE-M and NB IoT are popular energy efficient standards for wide coverage. Other technologies such as Bluetooth and Wi-Fi are used in local applications but have limitation in scalability and power consumptions. For large areas with many devices, LP1 technologies such as LoRaWAN and Sigfox are well connected over a cellular network, which reduces the risk of signal loss and ensures compatibility between different devices. Therefore, the use of the LoRaWAN standard is more appropriate in our opinion. Thanks to energy-efficient protocol, LoRaWAN-based devices can operate on a single battery for several years, making them ideal for remote sites. A LoRaWAN network consists of following elements: an end device, gateways, a network server, and an application server. In a LoRaWAN network, end services perform measurement or control functions and transmit data through gateways and that provide radio communication and access to the transit network. The entire system operates in a start-to-star topology, where the network server manages the network and the application server controls the devices and collect data. LoRaWAN has significant advantages: long range, low power consumption, good signal penetration, and no spectrum licensing costs, making it attractive for large-scale IoT solutions. However, the technology has limitations: low throughput, data transmission delays, spectrum interfaces risks, and the use of proprietary modulation. The greenhouse monitoring system is built on this basis of IoT sensors and the LoRaWAN protocol, where data is transmitted through a gateway to the IoT server. The LoRaWAN gateway provides communication between devices, and the server performs control protocol translations, adds layers of security, and supports of efficient operation of devices with limited resources. The IoT server, as is located on a virtual computer, is accessible for anywhere in the world via browser and allows users to create their own control panels and rules. This slide shows a sensor board for 3 temperature and humidity measurement points with the sensors using the one-wire protocol. This sensor is made in a moisture-proof housing with IP65 and powered by a 3 to 4.2 volts power supply. With minor changes to circuitry, the sensor allows you to connect up to 3 air or soil temperature and humidity sensors. Unique serial numbers allows multiple sensors to be connected to a single one-wire bus without conflict. The sensor consumes very little power, making it suitable for standalone devices. The sensor transmits the measured temperature in digital format, eliminating the need for additional signal conversions. The sensor DS18B20 is ideal for applications where accuracy, ease of integration, and low cost are important. However, for tasks with a high requirement for data speed, or in extreme conditions, its limitation must be taken into account. The sensor, designed to save power supply change, measures temperature no more than 1 minute, depending on settings, and upload data to the server when 10 values are accumulated. The sensor settings have upper and lower limits. If the temperature does not meet these limits, the sensor immediately uploads the temperature values and the status of the accident to the server. In turn, the server immediately informs the user about accident using messages in the cross-platform messenger Telegram until the user confirms receipt of the message. This is a great advantage of using IoT technologies in smart electronics. ThinkBoard is a scalable and open IoT platform that allows you to quickly create, manage, and scale IoT solutions, providing infrastructure both in the cloud and on premises. It supports data collection, processing, visualization, device management via various protocols, and has a power rule engine for event proceeding. Thanks to its flexible architecture, high fault tolerance, and extensive customizing capabilities, ThinkBot is suitable for projects of any scale. ThinkBot provides flexible visualization of technological parameters using built-in and custom widgets updates adapted for different devices. Based on the example of greenhouse monitoring and interface with customizable elements that display temperature and allow data analysis in the form of graphs was created. This project allows students to gain practical skills and meet the requirements of Industry 4.0 and modern productions. This slide shows the settings screen. It shows the sensor name, which can be configured on the server in the server attributes section or obtained directly from the sensor. Also, the sensor status is active or not, which is related to the time of the last telemetry. Setting the upper and lower limits is required for Telegram messages and changing the color of the widget on the home page. On this slide, we see the display of the sensor temperature change. We can select the time period for display. The maximum archive depth is currently limited to 90 days. We can display several dependencies of measured values for comparison or analytics. We also see the configured limits. The developed smart system for monitoring greenhouse climate uses wireless LoRaWAN and IoT technologies, providing automated microclimate control and convenient data visualization. It is an effective educational tool for students and in the future can be basis for integrating IoT and artificial intelligence and machine learning to create adaptive agricultural systems. Thank you for your attention.
Thank you for your presentation.
We see that there is one question from the auditorium. Mikhailo Krylov,
please.
You're welcome.
Hello, dear colleagues. I have the following question. On your opinion, what kind of equipment is the best for supporting temperature in this kind of premises? Because from my little experience, if we talk about the living quarters, so we have two opposite technologies, heating and cooling. And it's not the best solution for smart homes. The best solution is fan coils. But in this case, what kind of equipment you suppose it's supposed to use for supporting temperature? Thank you.
Fellow colleagues, I'm one of the co-authors of this thesis, so I will ask. Now our system is designed for monitoring and awareness for the users. And our greenhouses will have some special mechanism which will be monitoring and acting with special servo drivers, and some windows will open and close if it will be need. We know that sometimes the temperature in the greenhouses is higher when the sun is shining brightly, and then we need some system for creating a shadow for these greenhouses. And in other cases, in the night, sometimes the temperature is lower than the normal level is. And that's why special people should provide their needs level of the temperature using special system of warming. And that's why there are different types of mechanism for leveling the temperature in their proper range.
Thank you. Thank you.
Thank you. Are there any questions? Maybe somebody would like to ask. If no, then one question from us, if you don't mind. So you are using the encrypted LoRaWAN protocol, and the question: what server do you use to decrypt packets from the gateway?
Yes, we use the LoRaWAN protocol, which encrypts all transmitted data to insecure secure communication. To decrypt these packets which are received from the gateway, we currently rely on open source LoRaWAN network server, which names Chirp Stack. This server is hosted locally on our infrastructure and works in parallel with Things board. You can see their windows of this board in the slides. Chirp Stack handles the LoRaWAN network layer, including decryption of the packets, device activation, and message forwarding to application servers like Things board.
Thank you.
Yes, yes, thank you. So for today, for this session number 2, this was the last presentation. So thank you very much. Thanks to everyone who joined to this conference and to this session. Now we'll have a break till 3 p.m. And after this break, we will continue but with the session number 3. So thank you, thanks to everyone. We'll have some time for rest, and then we will continue. So thank you.
Thank you. Bye-bye.
Bye. А,
Выключи этот. Да. We start our section number 3, innovative aerospace technologies, and on managed aerial vehicles.
So during this session, we will have 5 presentations, and let's start from the first one on the topic methodology for assessing the efficiency of generated UAV flight route plans for optimal selection. From the authors, Alina Artemova and Igor Artemov.
Dear colleagues, today I will present an overview of methodology for assessing the efficiency of generated UAV fly route plans for optimal selection. Modern UAVs are widely used in various fields, such as monitoring, mapping, security surveillance, and cargo delivery. The effectiveness of task execution largely depends on the accuracy and optimality of fly route planning. However, existing methodologies often have limitations in terms of adaptability to changing environmental conditions, time and energy constraints, which leads to reduced resource utilization efficiency. Particular attention must be paid to the complexity of terrain, obstacles, restricted zones, and fly safety risk. This necessitates the improvement of route planning methods, which should integrate modern optimization algorithms and information technologies to enhance the speed and accuracy of calculation. Therefore, the development of a new methodology for evaluating route effectiveness is relevant, one that incorporates a comprehensive approach to UAV flight management. The problem of UAV fly route planning has been extensively studied by both foreign and domestic researchers. The problem of fly route planning for UAVs is one of the most important and relevant topics in the field of aviation and robotic technologies. In particular, route planning for object search is a crucial aspect of many missions, including monitoring stationary objects, observing dynamic targets, and resource preservation under changing constraints. UAV route planning is a complex process requiring various methods and algorithms, including traditional and intelligence approaches. The most promising methods allow for route adaptation to changing conditions and coordination of multiple UAVs to maximize mission efficiency. The distribution of resources and institutions across countries involved in UAV route planning can be estimated based on scientific achievements and investments in UAV technology development. UAVs can be classified into various categories based on route planning factors. Application: military. Routes for military missions often require high confidentiality and avoidance of restricted access zones. Civilian, used for applications like aerial photography, environmental monitoring, search and rescue. Routes are established according to client needs and safety zones. Size and range. Short range. Direct routing is suitable for short flights over small distances. Micro. Small in size with limited fly range. Nano. Even smaller in size and typically limited in functionality. Small, used for missions such as surveillance or reconnaissance. Long range. Detailed planning is required for flights over long distances. Medium light fixed wing, effective for long endurance fly over large distances. Quadrocopters utilize a multi-rotor design for stable flight over short distances. Helicopter-like features similar to helicopters with one or multiple main rotors. Hybrid models combining different flight types to optimize flight quality and fuel efficiency. Technology used: autonomous, capable of performing tasks without direct operator control, remotely piloted, require direct control or supervision by an operator. UAVs may in route planning. The developed methodology is universal and recommended for use with both military and civilian aircraft of any design and fly method. It is particularly relevant for route calculation over short distances, as it does not account for the possibility of planning stop points for recharging or refueling. The procedure for assessing the efficiency of the flight route scheme of a Class 1 UAV, taking into account the determinate indicators from the moment of receiving the task until the moment of UAV takeoff, includes next stages. Definition of factors for evaluating UAV fly routes. Definition of efficiency criteria for UAV fly route planning. Calculation of the absolute value of the aggregated efficiency indicator. Calculation of the normalized value of the aggregated efficiency indicator. Evaluation of the effective UAV route plan. The methodology covers various groups of parameters necessary for evaluating the fly routes of UAVs. For a comprehensive assessment of the effectiveness of UAV fly route planning, the following indicators are recommended. Route planning efficiency. A. This assessment includes factors: route length A1, minimizing the distance traveled to reduce resource consumption and enhance the efficiency of UAV utilization. Mission time A2, the time required to complete a mission, including maneuvers and stops. Mission cost A3, the cost of resource including electricity, UAV depreciation, and personal expenses. The goal is to minimize these costs. Regularity and reliability. B. Evaluation of the frequency and stability of route extension. Mission frequency B1, the frequency of completed planned flights. Maximizing this ensures stable task execution within the scheduled time frames. Interruption in missions planning and execution. B2, the frequency of equipment or software failures. The aim is to minimize such interruptions. Average missions preparation time, B3, the duration of the route planning process. Minimizing this ensures faster responsibilities for operation needs. Mission success, C, evaluation of how successfully a specific task assigned to UAVs is executed. Accuracy of collected information, C, minimal deviation of the actual route from the planned one. Emergency response and adaptability, C2, the ability to modify the route in real time in case of unforeseen circumstances such as weather changes or obstacles. Delivery and distribution of necessary materials, C3, maximizing the capacity for efficient logistical operations. Safety, D. Flight safety evaluation includes quantitative and qualitative indicators considering technical, operation, and environmental aspects. Risk of collision with other aircraft, D. The goal is to minimize the threat of losing the UAV or mission. Risk of communication loss, D2. Mission the risk associated with losing control of the UAV. Confidentiality and data security, D3. Ensuring the highest level of protection against unauthorized access to data. Hazardous weather conditions, D4. The ability of the UAV to perform tasks under challenging conditions such as strong winds, rain, or temperature fluctuation. Maximize these capabilities is crucial. Energy efficiency, E. Evaluation of how successfully a specific task assigned to UAV is executed. Fuel of electricity consumption for mission execution, E1, minimizing resource consumption to improve cost efficiency. Fly range and duration relative to energy consumption, E2, maximizing flight duration or task completion without the need for refueling or battery replacement. Based on the above, we present the expression for calculating the route efficiency in the following form. Where the efficiency planning criterion can vary with a specific range of possible values of fly route planning criteria, constrained by the conditions of performing a reconnaissance mission with a UAV system. The advantages of the chosen optimization scheme also include the presence of weight coefficient for the preference of indicators. This coefficient allows the person planning the fly route to retice and efficiency indicator depending on the specific task being performed. They are not equal and depend on the number of the indicators. To make a decision about the effectiveness of the plan, it is necessary to transition from the absolute value to the aggregated efficiency indicator to a linguistic category such as good-bad. The normalization of route efficiency score can be performed using the following expression. This is achieved by normalizing the evaluation criteria values within the range of 0 to 1, with the best value set to 1 and the worst value set to 0. The normalized aggregated indicator is assessed according to a linguistic scale for evaluating the effectiveness of the UAV fly route plan. From 0.7 to 1 is equals to high efficiency. From 0.5 to 0.7 is equal to good efficiency. From 0.4 to 0.5 is equal to satisfactory efficiency. A Java program was developed to evaluate the optimal route, considering various combinations of factors for each parameter used in the calculation. The study demonstrates that the success of mission execution for UAVs heavily depends on the effectiveness of live route planning. Modeling route effectiveness through aggregate indicators not only facilitates the evaluation of individual route alternatives, but also enables the selection of the most optimal route for mission execution. Thank you for your attention.
So thank you very much. And traditional question, and I see
Mikhailo,
Mikhailo
Okay,
have a
question.
question, so you're welcome.
The question
Mikhailo,
is
1 minute,
the
please.
following. Do you hear me?
No. It's just the question. Do we have here the presenters? Because we saw the video records,
Okay.
but is there Alina Artyomova or Igor Artyomov?
I'm sorry if I may interject. I know that Ihor got delayed working on the simulator and he was going to do his best to connect, but apparently that didn't happen. So I know that in any case, they would be happy to answer any questions by email, but unfortunately it seems that they were unable to personally connect.
Okay.
Okay. So let's move on.
No questions.
Yeah, so the next scientific work on the topic methodology, the topic is information transmission methods for coordinating and controlling UAV swarm flights. Authors Yegor Sopov, Alina Artyomova, and Hanna Miroshnichenko.
Ladies and gentlemen, esteemed colleagues, allow me to introduce myself. My name is Yegor Sopov, and I'm a postgraduate student at National Aerospace University Archive Aviation Institute. I am honored, and I would like to thank you for this opportunity to present our research on information transmission methods for coordinating and controlling UAV swarm flights, which I've conducted alongside my scientific advisor Alina Artyomova. This study examines communication models and routing protocols for effective swarm coordination. Let's begin by exploring why this topic is important in modern applications. So once again, today I will talk about the key challenges and approaches in organizing information transmission within UAV swarms. The systems are becoming ever more widespread in areas such as surveillance, disaster response, and agriculture. However, reliable real-time communication remains a major obstacle. Traditional centralized architectures are often inflexible and prone to single points of failure, while large-scale UAV networks require scalable, low-latency, and energy-efficient coordination methods. In this research, we aim to address these critical challenges. The general aim of our research is to enhance UAV swarm coordination. To do that, we completed several tasks. First, we reviewed existing architectural approaches. Then, we categorized routing protocols. And we also modeled 3 control strategies and tested them in simulations to measure performance. Our goal was to identify a model that balances resilience, speed, and energy efficiency. Now let us discuss the methodology used in this study. We focus on evaluating 3 major communication models. First, the traditional centralized model is where a single UAV acts as a control hub for the swarm. Second, the decentralized model is where UAVs communicate directly without a leader. And finally, the hybrid model combines elements of both to improve performance. Routing is a major challenge in UAV networks. To address this, we analyzed 3 primary categories of routing protocols. First, topology-based routing, like optimized link state routing and ad hoc on-demand distance vector protocols, uses predefined paths between UAVs. Second, geographic-based routing, like greedy perimeter stateless routing and geographical load share routing protocols, leverages GPS location for dynamic routing. And finally, swarm intelligence-based routing, like ant colony optimization algorithm. It mimics nature-inspired behaviors for adaptive routing. So, in order to validate these methods, we conducted simulations in Capella Sim, a widely used tool for robotic swarm modeling, and then the collected data was analyzed using MATLAB and Python to measure performance metrics. Our study focused on 3 key parameters: transmission delay, which is critical for real-time UAV coordination, packet delivery ratio, which ensures successful message transmission, and finally energy consumption, which determines network longevity and efficiency. As I mentioned, we began our research by evaluating the 3 existing UAV communication architectures. First, the centralized model, in which a leader UAV controls the entire swarm, ensures precise coordination, but it is vulnerable because it introduces a single point of failure. Second, decentralized mode, in which UAVs communicate peer-to-peer without a central controller. It has high fault tolerance but requires complex synchronization mechanisms. And finally, a multi-layered model is a hybrid approach, combining centralized oversight with local UAV groups. It balances efficiency and adaptability, but requires sophisticated routing algorithms. Now, let's talk about communication between the drones. This figure illustrates a single group swarm ad hoc network, where UAVs operate within a decentralized system to maintain efficient communication. The top section highlights different swarm formations, demonstrating how topology affects data transmission efficiency. The bottom section shows 2 network models: direct ground communication and inter-UAV relay networking. The importance of this approach lies in its ability to function without external infrastructure, ensuring resiliency and adaptability in dynamic environments. However, while this model enhances scalability and mission flexibility, it also introduces challenges related to network synchronization and routing optimization, which we will address in the next section. Efficient communication within a UAV swarm depends on robust routing technologies that determine how data packets are transferred between UAV nodes. This figure illustrates 6 fundamental routing technologies for UAV swarms, each designed to address unique challenges in wireless aerial networks. Store carry forward is a crucial approach for delay-tolerant networks, while greedy forwarding leverages geographic positioning to optimize path selection. More advanced methods like predictive routing and multipath routing introduce redundancy and intelligence to enhance UAV swarm coordination. However, each of these strategies has trade-offs in terms of energy efficiency, fault tolerance, and network overhead. Understanding these routing mechanisms is key to optimizing real-time UAV communication, and in the next section we will examine how these strategies perform in large-scale swarm simulations. This figure presents a classification of routing protocols for UAV networks, highlighting how different methods address communication challenges in dynamic swarm environments. Topology-based protocols establish and maintain structured routes, whereas geographic-based routing dynamically adjusts path using real-time location data. Swarm intelligence-based routing, inspired by biological systems, offers adaptive and self-organizing decision-making. However, each category presents trade-offs in terms of efficiency, overhead, and real-time adaptability. Selecting the most suitable routing protocol requires careful consideration of UAV network dynamics, latency constraints, and mission-critical requirements. In the next section, we will analyze the experimental results, comparing these protocols in real-world UAV simulations. This slide presents our experimental framework used to evaluate UAV swarm communication architectures in Capella SIEM. 3 models, centralized, decentralized, and distributed, were analyzed based on latency, failure resiliency, and energy efficiency. Centralized architectures offer strong control, but are vulnerable to single point of failure, while decentralized model enhance robustness at the cost of increased synchronization complexity. Our distributed model aims to strike a balance between scalability and fault tolerance. The insights from these simulations provide valuable guidance in designing more resilient UAV networks for real-world application. In the next section, we will examine the comparative results of these models. The effectiveness of a UAV swarm largely depends on its control architecture. This slide presents a performance comparison of 3 UAV swarm control models: centralized, decentralized, and distributed, evaluating their average delay, reaction speed, and failure impact. These metrics are crucial for understanding how each model behaves in dynamic environments, where real-time coordination and fault tolerance are essential. So let's look at the breakdown of the performance metrics. First, centralized control model has highest delay due to reliance on a single control unit. The reaction speed is slower due to bottlenecks in data processing, and in case of failure, the entire swarm stops. If the central UAV fails, all communication and movements halt. Second, decentralized control model features lowest latency as UAVs communicate directly. The reaction speed is also the fastest due to real-time peer-to-peer exchange. In case of failure, if individual UAVs are affected, the swarm remains functional, even if some of them fail. Finally, distributed control model features moderate latency due to hierarchical group coordination. The reaction speed is balanced compared to centralized and decentralized models, and in case of failure, swarm adapts dynamically. The network self-adjusts to failures, ensuring continuity. This table presents a comparative analysis of UAV swarm routing protocols, evaluating their performance in terms of delay, throughput, packet delivery ratio, and energy consumption. Traditional routing methods such as AODV and OLSR, while effective in structured networks, exhibit high latency and energy inefficiency when applied to UAV swarms. Geographic-based methods such as GPSR and GRP improve routing by leveraging positional awareness. However, the most promising approaches are swarm intelligence-based and reinforcement learning-based methods, which dynamically optimize routing paths. Our results indicate that reinforced learning-based routing significantly outperforms other protocols, achieving the lowest delay, highest packet delivery ratio of 97%, and most efficient energy consumption. These findings suggest that AI-driven routing is the key to enabling robust adaptive UAV swarm networks in real-world application. In the next section, we will discuss how these routing strategies impact real-time UAV mission performance. So, a short summary of our findings. The distributed control model is the most promising for real-world use. It balances coordination and adaptability. AI-based routing, especially reinforcement learning, significantly boosts performance in dynamic environments. Centralized control may work for small predictive missions, but not for real-time large-scale swarm operations. In conclusion, this study highlights the advantages of hybrid UAV communication models in enhancing swarm efficiency and resiliency. Among the routing protocols tested, reinforcement learning-based routing significantly outperforms traditional methods, providing the lowest delay, highest packet delivery ratio, and most energy-efficient operation. However, to fully leverage AI-driven UAV networks, future research must focus on real-world deployment and AI synchronization. The ultimate goal is to create fully autonomous UAV swarms capable of making real-time adaptive decisions with minimal human intervention. This research lays the foundation for the next generation of intelligent UAV swarm systems, bridging the gap between theoretical simulations and real-world implementation. We would like to express our sincere gratitude to the university and our department for their support, guidance, and access to simulation platforms. Thank you for your attention. I will now be happy to answer any questions that you may have or discuss further ideas.
Thank you for your presentation.
Yes, thank you. And traditional question is, are there any questions from the auditorium?
Mikhailo, do
Maybe
you
Mikhailo
have?
Prolog, do you have any question? If no, then we can ask. Okay,
No,
so
no, thank you.
Oh, yeah, we was sure that you will have a question. No?
No,
Oh, no, no,
Alina.
No, no,
sorry.
Thank you.
Dmitro?
Yes, I have
A question.
So I would like to ask, how do hybrid control models dynamically balance between centralized coordination and decentralized autonomy in real time, particularly under conditions of communication delay or node failure?
Thank you for your question. In general, like a hybrid control model whose goal is to combine the strength of both centralized and decentralized models means that certain tasks are generally inherently performed at different levels. Like global routing and mission planning are centralized, while local decisions like collision avoidance or trajectory correction, they're made autonomously by the nodes separately. And each node has special built-in algorithms for this purpose. For instance, like swarm intelligence algorithms like and colony optimization. However, if in case of communication breakdown, the whole system may switch to decentralized control model. And the main tool here, I believe, is network evaluation of network environment. Adaptive algorithms are usually used for that, and when the status of network, well, not when, the status of network is constantly evaluated, and if needed, the switch is performed between control models. And then the nodes can use the aforementioned swarm intelligence or consensus algorithms like Raft or Paxos to make decisions, or if all else fails, to resort to fallback. And same for node failure. Well, critical nodes usually have backups. The whole swarm can usually vote and elect a node for task assignment, for example, like a gateway node. If it fails, the rest can take a vote and select a new gateway node to communicate with centralized infrastructure. I hope I answered your question.
Okay, thank you for this answer. One more question. So what specific machine learning techniques were or could be most effective in enhancing routing protocol adaptability and decision-making within highly mobile UAV networks?
Thank you. Thank you for this question. Specific machine learning techniques were not the focus of this research, but I mean, of course, there can be many useful techniques depending on the task at hand and the specific environment. If I have to pick a few, I'd say, well, of course, reinforced learning first, because agents learn to interact with the environment and maximize the reward, which can be like reduced latency or energy consumption. Second is probably online learning and adaptive algorithms, because models are constantly updated based on new data, and this is critical for unpredictable conditions that we usually have at hand. And finally, I'd say graph neural networks, or GNN. We can present the whole network as a graph where nodes exchange information, and GNN can be used to predict topology changes and update routing as necessary.
Thank you. Thank you for your answer.
Thank you.
Let's continue. So the next presentation of the topic classification of autonomous UAV control systems review. The author Yevhen Щекольський.
Greetings, colleagues. My name is Yevhen Szczegolski. I'm a postgraduate student at the Department of Electromechatronics and Computerized Electromechanical Systems of Lviv Polytechnic National University. Today, I would like to share with you my research called Classification of Autonomous Unmanned Aerial Vehicles Control Systems Review. That's our agenda for today, and let's start from introduction. I think everyone felt that in recent years, the use of unmanned aerial vehicles has grown significantly across various sectors, and in the military domain, this growth is driven by large-scale global conflicts and the increasing technological sophistication of warfare. And this has led to widespread adoption of new solutions and approaches to UAV development. Beyond military applications, UAVs are also utilized in different fields, from healthcare to smart cities, from agriculture to logistics, all over the world. And the development of UAVs has significantly transformed approaches to performing tasks in various human activities. That's why effective UAV management requires modern systems that are adaptive to changing conditions and capable of operating autonomously. The purpose of this research is to systematize and classify existing UAV control systems to provide a clear understanding of their structure and functionalities. This in turn will contribute to the development of more efficient solutions for specific conditions and promote standardization in the field. Moreover, classification will help identify key research directions, which is crucial for the ongoing advancement of the industry. Each classification has its own criteria. In this case, the focus was on the autonomy of control systems, so the following classification criteria were chosen as level of autonomy, hardware and software architecture, control algorithms, and cybersecurity. So let's talk about each criteria in more detail. Levels of autonomy. Autonomy refers to the UAV's ability to effectively and safely accomplish specific tasks without human intervention. And UAVs with higher levels of autonomy can significantly improve the efficiency, accuracy, and speed of task execution. There are several primary classifications of UAV autonomy levels. The choice of classification depends on the app domain, the type of drone, and the specific research objectives. The most common classification are SAE, Society of Automotive Engineers, and ALPHOS, Autonomy Levels for Unmanned Systems. The SAE classification was originally developed for vehicle autopilot systems, but is often adapted to the specific features of UAV operations. And it's a universal system comprising 5 primary autonomy levels, shown on the slide in front of you. The central concept of this classification is the gradual increase in automated functions and the UAV's ability to make independent decisions. At autonomy levels 0, 3, the operator controls the flight, although the UAV may have stabilization systems, basic collision avoidance functions, or the ability to return to its launch point when communication is lost. However, at these levels, the UAV can't make autonomous decisions. At autonomy levels 4 and 5, the system is equipped with AI algorithms, enabling it to detect and recognize objects, determine the optimal trajectory, analyze the environment, and make independent decisions to achieve its goals. ALPHOS, developed by US National Institute of Standards and Technology, offers a more detailed approach compared to the SAE. And it considers the complexity of the environment, the mission, and the level of human involvement in the control process. So this classification includes up to 10 levels of autonomy. In addition to the mentioned classification, there are various military classifications of autonomy. They account not only for individual systems, but also for the ability to operate multiple UAVs of different types simultaneously. And military classifications are often more detailed and may isolate specific autonomous functionalities into separate categories, such as automatic takeoff and landing, obstacle avoidance, or other mission-specific elements. Regardless of the level of autonomy, any UAV control system consists of hardware and software components. And I will focus on higher autonomy levels because they are more complicated. And if we are talking about hardware, it consists of a propulsion system and a flight control system. The propulsion system includes a power supply unit, an electronic speed controller responsible for motor activation, and the motor themselves. The flight control system consists of a flight controller, an autopilot, and an additional computational module. The flight controller is responsible for basic computations to ensure stabilization and to process commands from the autopilot. Also, various sensors are connected there, such as cameras, GPS, barometers, and other equipment required for specific tasks. The autopilot typically is installed as a separate module, and its primary function is to manage the UAV according to the parameters of the assigned task. It maintains the specified attitude, direction, and speed, executes predefined routes, and other tasks. We have limited computing power of the flight controller, so are used additional microcomputers such as NVIDIA Jetson or Raspberry Pi, and these models process large amounts of sensors data and execute machine learning algorithms to analyze this data. Thus, the autopilot and flight controller are responsible for the UAV's movement in the environment, while the additional computing model handles the intelligent aspect of the autonomous system. As for software architecture, is divided into several layers, each comprising modules responsible for specific tasks, and together are responsible for general efficient and stable operation of the system. On slide you can see the hierarchy of these system layers. It includes the device driver layer, the operating system layer, the middle layer, and the application layer. The device driver layer is a low-level layer responsible for the operation of programs that directly control the sensors and actuators. In this case, it ensures the reading of data from the hardware. The operating system layer provides the necessary interface between the device driver and the higher-level software, essentially creating an environment for program execution. The operating system also allocates available resources among the modules and the use of real-time operating systems, enabling the simultaneous execution of multiple tasks. Middleware layer is responsible for the exchange and transmission of data between different modules of the system. For example, if the UAV system collects data from a camera, the middleware layer ensures its transfer to the processing module in the application layer. And finally, application layer. This is a high-level layer where complex functions are implemented, such as sensor data analysis, autonomous navigation, optimal trajectory planning, and analyzing output signals from AI for decision making. The next criteria is control algorithms, and they can be classified into linear and nonlinear, adaptive, and intelligent AI algorithms such as neural networks. The most common linear algorithm is the PID controller, and this approach works well in stable, predictable flight conditions, but they have significant drawbacks in dynamic environments, such as during strong gusts of wind, because we only control fixed P, I, and D components of the controller. And to overcome the limitation of linear controller are used nonlinear methods, such as sliding mode control, backstepping, model predictive control, etc. And these methods employ a significantly larger number of parameters for control correction and additional mathematical calculations, allowing for a more effective response to system deviation and improving the drone stability. Higher algorithm is adaptive. It's used when the parameter set of nonlinear algorithms is insufficient to account for system dynamics and there are parametric uncertainties. This algorithm automatically adjusts the controller parameters in real time to maintain system stability and optimal performance. And finally, when systems require greater flexibility and efficiency in complex dynamic situations, are used neural networks. They can learn from sensor data, create mathematical models that account for required characteristics, and predict potential future changes. Neural networks also contribute to optimizing the system and improving its performance. So, as you can see, adaptive control provides the foundational structure for stable system operation, while neural networks enable more detailed and efficient management of the system in unpredictable conditions and complex situations. The last criterion, but not least, I would like to present is cybersecurity. Ensuring robust cybersecurity in such systems is crucial. The level of challenges and protective measures in this field depending on the degree of human control over the system. And if we talk about low autonomy system, it relies heavily on continuous operator control via communication links. So the primary cybersecurity concern for these systems is the unauthorized access to control telemetry, which can lead to command interception or communication loss. To reduce such risks, it's enough to implement robust encryption protocols and authentication mechanisms. UAVs with conditional or high autonomy beyond communication link vulnerabilities are sensitive to software attacks targeting their autonomous functions. Typically, such systems are used monolithic architecture, where all processes run within single execution environment. And one of the main cybersecurity countermeasures in this case is transitioning from monolithic architecture to models, containerized environments using technologies such as Docker and Kubernetes. So in this case, an attack on one model doesn't affect the entire system. Fully autonomous systems face the most sophisticated cyber threats because it's possible to spoof sensor data from GPS or LiDAR, leading to incorrect navigation, etc. And in this case, defensive strategies should include multi-sensor data fusion techniques to cross-verify navigational inputs, redundant navigation systems such as inertial measurement units, and AI-driven monitoring to detect and counteract sensor spoofing attempts. In conclusion, considering the realities of drone usage in Ukraine due to ongoing war, further research should prioritize the development of higher autonomy level systems using adaptive control algorithm, supplemented with artificial intelligence depending on the task. And this direction will enhance the capability of UAVs to operate effectively in complex and dynamic environment, addressing critical challenges in both military and civilian domains. Of course, the future lies in autonomous systems, no matter how futuristic it may seem. Implementing autonomy may reduce the need for human control, which lowers operational management costs in the long term, and in terms of military use, can save soldiers' lives. But the cost of implementing autonomous systems often significantly exceeds the initial cost of low-level autonomy systems, making them less attractive for short-term projects. Therefore, we still have time before swarms of various types of UAVs fly over our heads without involving humans in their work. Thank you for your attention. I will be happy to answer your questions if any arise.
Thank you, Evgen, for your informative presentation. There are any questions from the audience? Mikhailo? No? Alina, do you have a question?
Yes, if there's no question from auditor, so we will ask. So the question, what criteria should be used to determine the optimal levels of autonomy for UAV deployment in different sectors, considering both operational requirements and economic feasibility?
Greetings, colleagues. Thank you for the opportunity to speak to you. And thank you for your question. So there are many criteria, actually, but first, I think it's mission complexity. The more unpredictable or dynamic the task, such as autonomous reconnaissance or target tracking, the higher the level of autonomy required. Secondly, it's, I think, the environment in which our system should operate. UAVs operating in urban spaces, dense forests, or GPS-denied zones. They must handle real-time decision-making and navigation, which calls for more autonomous behavior. And in contrast, open field operations allow for simpler systems. What else? I think human involvement it's not the last thing. If we could potentially have communication interference, human would not be able to control the system constantly, or with a delay, for example, then the UAV must make decisions independently. So this is especially relevant in military or remote applications. Also regulatory and safety constraints, because airspace laws may limit how autonomous a UAV can be, especially in civilian or densely populated areas. So some regions require human-in-the-loop systems for legal and safety reasons. I don't know what else. Of course, the economic component, right? High autonomy systems cost more upfront due to complex software, AI models, and cybersecurity. However, they may reduce long-term costs by minimizing human labor and increasing efficiency. So this is a significant criteria, I think. And finally, sector-specific demands. For example, agriculture often benefits from low to medium autonomy. Urban delivery may require conditional, and military scenarios typically demand high-level autonomy for fast and independent decision-making. Well, in our realities, most military drones don't have full autonomy, but let's return to the previous criteria: economic feasibility. War requires a lot of means of deterring the enemy for little money. Yeah, but ideally, so that our military doesn't risk their lives, a UAV with a high level of autonomy is the right choice. So, yeah.
Dmitro. And I have a small question for you. How do the proposed microservice architectures specifically enhance both scalability and cybersecurity in UAV control system compared to the traditional monolithic systems?
Monolithic and microservice. All right. Okay, so in terms of scalability, microservice architecture allows developers to scale only the services that require more resources without affecting the entire system. So it's very convenient. And for instance, for example, in the LIMIC project, which focused on autonomous UAV-based infrastructure inspection, microservices were used to separate and independently scale the path planning, image recognition, and I think data synchronization models. So this led to faster mission planning and more efficient traffic control because we are deploying these services in a Kubernetes cluster. From a cybersecurity side, well, microservices provide better isolation and protection against possible vulnerabilities. Because in such system, components such as the navigation model, sensor data parser, or user identification service run in separate containers. So if one model is compromised, it doesn't directly affect the others. So with tools like Docker and Kubernetes, it's possible to automatically isolate, shut down, or restart a hacked service without disrupting the rest of the UAV system, which is much more reliable than monolithic architecture.
Thank you very much.
Thank you.
Thank you. Thank you for your presentation, for your answers. And so we move on in the next presentation on the topic, analysis of modern approaches to occupation of aircraft parts, geometric data digitalization by reverse engineering, by the authors Katerina Mayorova, Igor Lysachenko, Alexander Skiba, Artem Suslov, and Viktor Antonyuk. So we'll start the video records and then we'll have some questions.
Aerospace manufacturing is characterized by a large number of parts with geometric accuracy within range plus minus 0.1, 0.3 millimeters. The quality indices such as reliability, efficiency, on a significant extent depends on the ensured geometric accuracy of the aircraft assembly components. For this reason, coordinate measuring machines are widely used in the aircraft production. The technology of reverse engineering based on the 3D scanning has become widely used in the repair and restoration of aircraft parts and the product as a whole. The major challenges of reverse engineering based manufacturing are the follows. In reverse engineering, there are two ways to create a digital model, so-called sustainable and conventional. Sustainable reverse engineering includes all the stages of digitalization with the point cloud final processing and creation of an aircraft part scan. It's so-called digital portrait of a part. In this case, the rapid production of the part according to the scan by additive technologies is assumed. Conventional reverse engineering include sustainable reverse engineering with additional stages where a CAD model, digital mockup, is rebuilt based on the obtained geometry of the aircraft part scan. In this case, using the obtained aircraft part digital mockup, any technologies of part manufacturing, including additive manufacturing technologies, may be chosen. However, all such solutions have the right to exist only on the condition that the obtained scan of the aircraft part will ensure the specified geometric accuracy and the quality of the part surfaces that manufactured according to it. Therefore, it's important to carry out full-scale approbation. That is to study of a full-scale sample by comparing its scan with the initial model of an aircraft part, which was created as a primary source of information. Their disadvantage in this case is additional expenses of costs and time both for testing, especially for aircraft parts with overall sizes larger than 150 millimeters. However, if this problem may be overcome, then the limit criteria with permissible deviation in the geometry of the manufactured part, both according to the digital mockup and according to its digital portrait of the aircraft part, became undefined. This is especially relevant when it's necessary to renew damaged parts of prototyping, those for which there is no both design and technological documentation. The main goal of this study is to determine the permissible deviation in the geometric dimensions of a part made according to an aircraft part scan or a digital model as a primary source of information. The aim and task of this research. The hypothesis of the research assumes that inspection of the geometric accuracy of the refined so-called ideal digital portrait can be provided using the acquired portrait of the experimental part, which was created using any technologies. At the same time, for large-sized parts, such verification is possible using an ideal portrait of the reduced size, provided that the tolerance of the rated size of the sample is determined. That is, in the absence of technical specification of the tolerance of form, orientation, lockout, runout, these deviations are limited by the size tolerance field from reference data generally accepted in mechanical engineering. The research is based on the general principles of production technologies of the airspace technology. During the work performing, the methods of general scientific and empirical research on analysis and synthesis were applied for the preliminary statement of the problem. The research was carried out as follows. First is design and technological analysis of the experimental sample. Second, choice of the scanning device for 3D scanning that ensure high accuracy of the resulted geometry. Next, processing the resulted scanned surfaces and creating a digital portrait. Next was creating a digital mockup from the geometry of the received digital portrait data and developing the part manufacturing technology. Next was making a decision on the tolerances values of the manufactured part geometry, and as final, analysis of the result and making conclusions. Research and discussions. The geometric accuracy of the manufactured aircraft part must meet the requirements for structural tolerance and technical requirements for production according to the conditions of operations of the part in airspace technology. In fact, the real geometric accuracy of the manufactured surface of an aircraft part is a difference from its nominal surface. That is, processing error is the deviation of geometric parameter of the part obtained during processing from the specified one. The value of the absolute error in units of considered part parameter is determined by a formula represented in the slide. It means that value of absolute error is the difference between real and nominal value of parameter, and the value of relative error is the ratio of an absolute error to the specified value of this parameter. As you might see in a formula in this slide, it may be represented in the fraction of the unit or in percent. And accuracy is characterized quantitatively by the inverse value of the relative error model. The main attributes of any solid body are the presence of two types of characteristics. First, it comes about geometry, and second is a set of parameters of surface material, physical and chemical ones, that depends on the point of measurement on the part surface. For studying the stated goals and solving the problem arising from this goal, it was quite sufficient the first attributes to use in the case of using the digital portrait of researched part. And for the case of using the digital mockup, it was necessary to consider two first and second parameter, first and second group of attributes. In tables first and second are presented the form tolerances for the flat and cylindrical surfaces, depending on the size, deviation, quality, grade, and degree of relative geometric accuracy. In table 1, as you might see, nominal size means the size of the largest side of a flat surface. And it should be noted that the values of form tolerances for cylindrical and flat surfaces, as well as the surface roughness values, depends directly on the quality grade of size tolerance and degrees of relative geometric accuracy. In table 2, nominal size means the size of the largest side of a flat surface, and table 2 shows the following. The nominal size means nominal diameter of the surface, tolerances of cylindricity, roundness, and profile of the surface corresponding to the levels A, normal geometric accuracy, B, increased geometric accuracy, and C, high relative geometric accuracy, which is approximately 30, 20, and 12% of the size tolerance. As a conclusion, it should be said that proving the obtained geometry for an experimental aircraft part of dimensions, overall dimensions larger than 100 millimeters in size, it's possible to implement reverse engineering when using 3D scanner with creation in the case of conventional reverse engineering aircraft part digital mockup, and in the case of sustainable reverse engineering, a scan of an aircraft part, so-called digital mockup. Production of a trial sample in a reduced size on a 3D printer inspection using the 3D scanner, taking into account the data determined according to the tables 1 and 2. Further research on the prototyping, repair, renewal of the geometry of these aircraft parts of complex profile and convex concave aircraft parts of larger dimensions will be directed to the studying and selecting the necessary equipment fleet, comes about scanners, printers, and so on, for the implementation of approbation, concluding full-scale experiments for specific dimensions of parts which has no design and technological documentation. Thank you for your attention.
Thank you very much for your presentation. And the first question that we have, so do we have the authors of this scientific work online here with us? Katerina Mayorova, Igor Lysachenko, somebody is here. So maybe not, maybe they have some troubles with the connection. So let's move on. And the last one for today, scientific work on the topic technological support for reverse engineering of parts using additive methods. So we'll start the video records and then there will be some questions.
Dear colleagues, we present to your attention a report on the topic of technological support for reverse engineering of parts using additive methods, based on research conducted at the National Technical University Kharkiv Polytechnic Institute together with an engineer from the Polish company Hermes Technic. The volume of repair and restoration work has been steadily growing since the 2010s after a long decline in the 1990s and early 2000s. Growth has been especially noticeable in recent years against the backdrop of automation, digitalization, and the need to maintain equipment, much of which is outdated and needs to be restored. Technical trends. Ability to create 3D models of a damaged part based on automation of measurement methods and correction of the resulting image. Development of additive and subtractive technologies based on the use of 3D models. Growth in the number and development of SME capacities related to reverse engineering. The study's main goal is to generalize existing technologies and evaluate new possibilities for reverse engineering of parts. To achieve this goal, the authors set themselves the following tasks. To analyze the existing problems of repair and restoration of parts. To systematize existing methods of restoring damaged and worn parts. To develop a general methodology for technological design and production in the process of reverse engineering. The method of questioning and processing of technical documentation was used as the main research method. In the period from 27.08.23 to 29.06.24, employees of the National Technical University Kharkiv Polytechnic Institute and a representative of the Polish company Hermes conducted a survey of enterprises in Kharkiv and Legnica, which operate various engineering products, as well as enterprises that are engaged in repair and restoration. The focus group was attended by directors, leading specialists, and managers of 28 enterprises of the machine building sector. Participants of the focus group of enterprises that operate various engineering products shared the problems and wishes they faced when repairing machines, and participants of repair enterprises talked about how these problems are solved and what methods of restoring parts are used in work. Some methods were tested and improved in the laboratory of the Department of Mechanical Engineering Technology and Metal Cutting Machines of the National Technical University Kharkiv Polytechnic Institute, NTUKHPI. In order to be able to use certain methods, various parameters of additive processing were analyzed, the material used and its physical and mechanical properties, ensuring geometric accuracy, the speed of reproduction of the object of the corresponding technology, the characteristics and cost of equipment, etc. As an example of summarizing the results of the analysis, the table presents comparative characteristics of the most common methods of additive processing. The technical characteristics of additive equipment, mainly for working with plastics, were analyzed. Snapmaker as example. The technical characteristics of additive equipment, mainly for working with plastics, were analyzed. Snapmaker as example. Based on the analysis conducted, a comprehensive methodology for the technical and technological preparation of the production of the restored part was proposed. In general, a formalized methodology for technological support of reverse engineering tasks includes a sequence of actions. The dark arrows show the process of coupling restoration using additive technology. The light arrows show possible options for using subtractive technology. Analysis of the part. Creation of 3D CAD models with corrective. Export this model to the CAM system. Equipment selection. Obtaining a control program or slider. Equipment preparation or adjustment, CNC machine or 3D printer. Part production. At the stage of obtaining a 3D model, a damaged or worn part is scanned by various methods from manual measurement or scanning to laser scanning on coordinate measuring machines of various types. It all depends on the geometric shape and functional purpose of the part. Processing of measurement results and construction of a 3D model of the object is carried out by software tools that are built into SIEMS by manufacturers, as well as by third-party programs for analyzing measurement results, Geometric Design X, Polyworks/Innovemetric, 3Drays Hyper-Reality Capture, etc., and extensions with the function of reverse engineering for the most popular CAD systems, Scan2 3D for SolidWorks, Autodesk Fusion 360, Siemens NX, Kasha, etc. Much attention is paid to the correction of measurement results, elimination of noise, and the development of a parametric model when creating a 3D model. This is especially important when creating a model based on the analysis of the parameters of a part that has lost its original shape, due to wear, breakage, deformation, etc. The software allows you to take into account damaged segments, symmetry of part elements depending on its functional purpose, the formation of the surface contour due to geometric primitives, in cases where this does not contradict the functional purpose. For example, the profile of turbine blades is built by smoothing without the use of traditional geometric primitives. The figure shows the sequence of restoration of the chain sprocket part, which had significant damage in the area of the hub and toothed profile. There was no drawing of the part, so a 3D model was initially created and corrected using a handheld scanner and the Geometric Design X system. At the next stage, based on the functional purpose and material of the part, it was decided to restore the part using the subtractive method on a multi-purpose milling machine. Next, a control program for processing the part was created and the processing was performed. As a result, a new part was obtained, which was subsequently installed on a chain conveyor. The next example is the creation and replication of robotic arm grippers for moving glass products. The body is made of ABS, and the damper is made of elastic thermoplastic polyurethane, a material with high flexibility and strength. It is chemically and vibration resistant, gives minimal shrinkage when cooled, which makes it a promising material for 3D printing. Thermoplastic polyurethane is widely used to create wearable components that retain their shape after deformation, which was the reason for choosing it as the most suitable material. An example of using both additive and subtractive methods for manufacturing structural parts in the process of reverse engineering is given. The basic elements of the equipment of the transport conveyors of the disposable tableware production lines were prefabricated. The central part is made of aluminum alloy with overlays made of plastic, polyethylene glycol, which made it possible to significantly reduce the metal and labor intensity of production. Moreover, on the basis of general 3D models, the aluminum alloy part is made on a CNC machine, and the overlays are made on a 3D printer. Overlays, performing, among other things, a protective function, are essentially consumable elements reproduced by high-speed 3D printing. Moreover, the presence of the created 3D model allows you to manufacture this consumable at almost any time at minimal cost. Reverse engineering significantly reduces the labor intensity of repair work, regardless of the methods of restoration of parts, additive or subtractive, ensuring the necessary accuracy and functionality of the restored product. At the same time, it is possible to create sets of models and documents for the same restoration work in the future. The authors propose an enlarged method of technical and technological preparation of production for the performance of repair and restoration work on the manufacture of parts, for which there is no technical documentation. The preparation process is divided into complete stages, which allow you to carry out the entire path of preparation from analyzing the condition and creating a 3D model of the part to obtaining the finished product. The recommendations proposed by the authors for the organization of repair and restoration work of engineering products are focused primarily on small and medium-sized enterprises that are engaged or plan to engage in such work in the future. The authors express their deep gratitude to the management of Hermes Technic in Poland for the active discussion of methods for building 3D models of worn parts based on object scanning data. The authors also express their deep gratitude to the management of the Coda Enterprise for consultations on methods and software products for suppressing noise and correcting 3D models of scanned parts.
Thank you for your presentation.
Yes, thank you very much. So this was the last presentation for today in this session. And now I'm almost sure that we have a question from auditorium.
Mikhailo, please.
I'd like to ask if there is somebody whom I may ask the question.
Yes, I would like to answer your
Well,
questions.
Okay, thank you. The first thing is the problem of reverse engineering, that we do not have any drawings. It's the first. The second, when repairing, we have worn surfaces. And how to take this fact into account in order to preserve the character of joint? What should we do in this case?
Well, first stage is we need to analyze the part. So, after analyzing the parts, we can basically use norms and ethos and so on to determine what was the weird surfaces was. Is it like a weird shaft or a gear or any kind of stopper moving parts whatsoever? So determine the part, we can after this determine the measurements, and so we can use conventional methods of 3D modeling or 3D scan if our part is not damaged so much. So we bring up a model, and after this we can manufacture the part exactly the same it was before.
But excuse me, how can you find the initial size of this part and tolerance for this part? Because you're modeling and scanning worn part.
Yes,
that is
but in determine if we know what exactly the part is this. For example, it was a shaft, yeah, some kind of shaft that are spinning on the conveyor or something. So and if we know this is a shaft, so we know how to say, perform with some kind of bearings or some kind of gears. So if we know exactly this is a shaft that rotates on bearings and apply momentum from the gears or whatsoever, we can use normalized surfaces from the ISO, DIN, or ASRs whatsoever.
Okay, thank you. Thank you.
Thank you, Tom.
So, okay, are there any other questions from the auditorium? So if no, so thank you very much for all these presentations, for being with us during this day of our conference. And I think that we can finish for today, and the next or the continuation of our conference will be tomorrow from 10 a.m. till 12 a.m. We will have session 4, Modern Electrical and Energy Systems. So it will be the last session. So thank you very much to all of you for being with us. Have a good day, and see you tomorrow.
Goodbye.